Alright, so not all sequences are going to be arithmetic. Some are going to be what we call geometric. Okay, now consider this sequence right here, 3, 6, 12, 24. How is this different? Well, we can see hopefully pretty clearly that it is not increasing by a common amount. In other words, we don't have a common difference. So this can easily be shown by subtracting our terms and showing that 6 minus 3 is not the same as 12 minus 6, which is definitely not the same as 24 minus 12. That was our test for finding a common difference. So it's not arithmetic. Instead, it's geometric, because if we look at this right here, notice that we would have to multiply by 2 to get the next term. That pattern's pretty obvious. So it's different in the sense that we have a factor that we would have to multiply each term by to get the next term. Well, we call this the common ratio. And we're going to use a lowercase r to represent the common ratio. And the idea here is, since it's a ratio, it's a fraction, if we were to work backwards, just like we work backwards with arithmetic, but instead of subtracting, if we worked backwards and divided, notice that 6 divided by 3 is the same as 12 divided by 6, which is the same as 24 divided by 12. All right, you get a common ratio of 2. And again, we're going to use a lowercase r to represent that. Okay, so with a geometric sequence, it's actually growing exponentially. Okay, terms are getting very large very quickly. All right, well, that is at least if the r value is greater than 1. So suppose we wanted to find the 11th term. Well, we have another given formula. This is the third given formula that IB gives us for sequences in series. We have 2 for arithmetic and we have 3 for geometric. So here's the first one, and it's very similar to the one that is given to us for arithmetic. If we're going to use this formula to find the 11th term, we're really trying to find u sub 11. So it tells us in our formula first we need u sub 1, which is our first term. So that's 3. Then we see that it's multiplied by r. Well, our common ratio is 2. And then it's raised up to the n minus 1 power, so that's 11 minus 1. So if we clean this up, we have 3 times 2 raised to the 10th. Now, beware, be on the lookout for this rookie mistake. This right here is not equal to 6 to the 10th. Okay, you cannot do that. Instead, this is equal to 3 times, now if we do 2 to the 10th, that's 1024. So that has to be done first, and then we multiply by 3. And that'll give us 3072. So the 11th term, if we were to continue out this pattern, would be 3072. All right, let's move on. Now we're looking to find the sum, just like we did with arithmetic. Suppose we want to find the sum of a finite number of terms. Okay, well, we have 2 formulas here. They're basically the same formula. The only difference is on the inside you have r to the n minus 1, and then you see the reverse of that, 1 minus r to the n. So very, very similar formulas. Doesn't matter which one you use. All the variables are the same in each formula. So now we're going to look at a different sequence here. 2, 6, 18, dot, dot, dot. Well, notice that the common ratio is 3. It's pretty easy just to look at it and see that, okay, I'm going to have to multiply by 3 to get the next term. Okay. By the way, if the common ratio were negative, your terms would alternate in sign. Okay, sometimes you will have a negative common ratio. If you have a common ratio that's a fraction, your terms are going to go down. That is, if the fraction is less than 1. So back to this, we're trying to find the sum of the first 9 terms, so we write this as s sub 9. Let's use this first formula here. So we need our first term, which is 2. Then we have r raised to the n, so we established that the common ratio is 3. We want to raise it up to the n. Well, if we want the sum of the first 9 terms, that means that n is 9. Okay. Then we see minus 1. Now the minus 1 is not part of the power. Back up here with our formula that we saw earlier for finding any term, u sub n, the n minus 1 was all together as part of the power. Whereas back here, we do not have that negative 1 as part of the power. Okay, so it's just 3 to the 9th and then minus 1. And then, again, just plug into the formula. Our value we said was 3 minus 1. Well, if we clean this up here, you're going to have a 2 in the bottom, which will divide out that 2 up top, leaving us with 3 to the 9th and then minus 1. So when we do 3 to the 9th and then subtract 1, we're going to get 19,682. So if we were to add up our first 9 terms in that sequence, that's what we would get for our sum. Alright, last section here. Suppose we want to find the sum of an infinite number of terms. So if I were to continue the pattern indefinitely, so if I go back up here to look at this example, if I were to just continue that pattern on and on and on and on, and if I were interested in finding the sum, well, it wouldn't really make sense to use the example up here because my terms, it's pretty obvious, are going to be getting huge very quickly, and if I were to try to add up an infinite number of terms, my sum would just be infinity. So what we need to think about in order to use this final formula here for the sum of an infinite number of terms, we have to get a feel for what r would have to be in order to get a finite sum for an infinite number of terms. So if r is 3, our terms are getting big very quickly. Earlier we saw r was 2. Same thing, terms are getting pretty big pretty quickly. Well, what if r were 1? If r were 1, well, if you're multiplying by 1, then your terms are just staying the same. Well, hopefully it makes sense to you that if r were less than 1, well, something like a half or a quarter or a third, well, then your terms would be getting smaller and smaller and smaller and smaller. So if we're going to get a finite sum for an infinite number of terms, our r value would have to be less than 1. And I'm going to slap an absolute value sign around that r value because technically we can have negatives, okay? But to make it simple, let's assume that r has to be positive. So the absolute value of r would have to be less than 1. So in other words, you want a fraction less than 1. Okay? So let's take a look at this example here. We're looking to find the sum of this sequence. And notice we have terms that are getting smaller and smaller and smaller and smaller. Our common ratio would be 1/2 here. And again, if you're having trouble seeing that, just work backwards and divide. Okay, 8 divided by 16, which is the same as 4 divided by 8. All right, if you were to work backwards and divide, you're always going to get your common ratio. So we have a pretty simple formula to use here. The sum of an infinite number of terms, so s sub infinity, that means the sum of an infinite number of terms. That is equal to u sub 1, our first term, which is 16. Here's our first term, divided by 1 minus the r value. So it's a pretty simple calculation. You have 16 divided by 1/2, which is the same as 16 times 2, which gives us 32. So what this is saying is if we were to add up an infinite number of terms, our sum would be 32. And let's just take a look at what we have here. We have 16 and 8, that's 24. If we add 4 more onto that, we're at 28. Add 2 more onto it, there's 30. Plus 1 more, it's 31. So if we add just the integers, we're at 31. If you were to then add all of these fractions, which are getting smaller and smaller and smaller, closer and closer to 0, hopefully it makes sense to you that the sum here would be 32. after a while we're adding something on that's basically 0. So that sum is going to kind of level off.